electrical engineering major, and as mentioned, I'm going to San Diego in 2 weeks.
And hi, my name is Oteti. I'm pre-med biology first year here at Foothill, and I'll be returning in the fall.
And yeah, we were process associate interns at a company called Intermolecular. We were part of the metrology team, and it is a research and development company. And well, first of all, we worked with semiconductors, and who even cares about those? Well, actually, everyone cares about them. So consumers, companies like Nvidia, Apple, Intel, and also governments. There's a lot of geopolitical things going on in the Pacific between the United States and China with Taiwan because of semiconductors. And well, semiconductors are metals that are used to make the circuits and electronic devices. Semiconductors basically make all electronic devices, computers, cell phones, satellites, medical equipment, you name it. And they also enable certain infrastructures like communication infrastructures and defense systems. And like I mentioned, we were part of the metrology team, but what even is metrology? Well, metrology is the science of measurements. It establishes standards in measuring. It makes sure that measurements are accurate. It ensures reliability of the measurements and, most importantly, repeatability of measurements. And in the semiconductor industry, metrology helps with thin film properties. Specifically, semiconductors require very thin films of materials, and so metrology helps measure those, make sure that they're uniform, and it gives this data to engineers or the projects that are using these materials. And metrology also helps with process control. So all these materials are going through many different processes, machines, going through different chemical reactions, and metrology helps make sure that they're all uniform, that they're all efficient, and they're all working as intended. But most importantly, it measures electrical properties of these semiconductor materials. None of these materials would be helpful if you couldn't make electronics with them, and metrology is a critical role in measuring those things. Now, some more background information. We worked with semiconductor chips, wafers, and coupons. The wafers look like this almost plate thing over here, and the coupons would be cut from them. Coupons are like smaller squares cut from these big wafers. And the atomic properties of these semiconductors, well, they are crystals. So their atomic structure looks like this model right here. The atomic structure is uniform, and metrology helps with measuring the atomic structures to see what kind of structure is there. It also measures defects in the materials and just also what kind of materials are in there after certain chemical processes. And because these are extremely thin films, we don't want particles going on top of it and interfering with the measurements. So we worked in a clean room for the 9 weeks. We would have to put on gloves, shoe covers, face masks, and hairnets. And then once we put that on, we would put on these plastic suits to cover our entire body. And there were over a dozen machines that we would work with. However, we specialized in two. The first one is the XRD machine, an X-ray diffractometer. And this machine had two different measuring processes. It had the XRD measurement, which is X-ray diffraction. So in this machine, we would load the wafer onto this pedestal and secure it with a vacuum tube. And then we would put in these like metal rectangles with slits in them so that the laser can pass through it. And so then it would shoot a laser into the material, an X-ray laser into the material. The X-rays would interfere with the material and diffract outwards. And then this piece would measure it at different angles. And so the XRD process would tell you about the crystal structure of the material, any defects in it, and the crystallinity of it. The second measuring process is the XRR, the X-ray reflectivity process. And with this process, it would shoot X-rays onto the material at angles before diffraction would start. And then it would get those X-rays reflecting off of it. And with that data, it would tell you the film thickness, the film density, and the surface roughness. Both of these processes would be done onto the same wafers, just so you can get all this information at once, and then we would send it to the different projects that would be working with those materials. Now for the second machine, Oteti will explain it.
So like the XRD, the WD-XRF, or Wave Dispersive X-ray Fluorescence machine, is also a critical tool in semiconductor engineering, which is used to determine the chemical makeup of wafers. So by directing a beam of X-rays onto the wafer, atoms within the material become excited and release secondary radiation that is characteristic of each element. So these signals reveal both the identity and the elements present. The technique is non-destructive, making it ideal for measuring film thickness, confirming uniformity, and supporting strict quality assurance without damaging the product. This efficiency and accuracy have made both the WD-XRF and XRD machine a cornerstone in advanced chip fabrication. So unfortunately, we don't have any results for you to see, as the data and information we obtained is confidential within the company. But as such, the outcome of our work extends beyond technical results, because Alan and I gained hands-on familiarity with the research and development cycle, seeing how an idea can progress into a valuable solution. The process also required structured planning and constant refinement, mirroring the standards used in professional settings. And this experience not only provided us with valuable technical skills, but also highlighted how persistence and iteration contribute to meaningful discoveries. And more than anything, it reinforced the link between classroom learning and real-world applications that shape modern technology. So in conclusion, our work centered on making sure each process ran without issue, was efficient, and was exactly as planned for each project. So by collecting and distributing data from each machine that we worked on through our work on wafers, we kept the cycle of research moving forward in the development cycle. So by doing so, we were able to contribute to the overarching goals of the company. And so our key contributions led to increasing manufacturing yield, shortening the development cycle for new designs, and also reducing costs so advanced technology can reach a broader market. And to achieve these objectives, we helped the MD pursue 3 different approaches, which was also advanced packaging for compact and efficient layouts, heterogeneous integration, and different companies also combine like different components into a single system. And also optical data for using light for greater transfer speed. And together, these strategies aim to create chips that are not only more powerful, but also widely accessible. And so working on this project gave us direct exposure to research practices and taught us how to carry out careful testing and problem solving. And the experience strengthened our enthusiasm for science and engineering by showing how physics and material science converge to push semiconductor innovation forward. And we also met and worked with many different employees from different teams, and were able to network with them. And some of those people we've also met happened to be prior Foothill students, and even people from this same internship years ago. And so Alan and I developed a clear view of how industry functions from top to bottom, and overall, we came away with a greater appreciation for how research drives industrial progress and creates benefits for society as a whole. And we couldn't do this without our superiors at Intermolecular, so we'd like to thank Samira for taking us in and introducing us to the corporate world of semiconductors, and as well as being a voice of encouragement in our life pursuits. We love her. And we also greatly appreciate Emmanuel for being our guiding hand as he taught us how to operate all the various machinery, and being our mentor as we sought to develop our skills. And lastly, we'd like to thank Peyton for being our guide and giving us valuable insight and information in the world of semiconductors. We'd also like to thank our team back at Foothill, Sophia, Donna, and Daniel, and all those behind the scenes for helping us throughout our internship and for counseling us throughout our time here. Thank you so much.
And thank you to all the donors who made this internship possible and that helped make this program. Without you guys, we wouldn't have gotten this experience that honestly helped us either reinforce our love for engineering, or maybe even showed us that we might not like to do it. But yeah, thank you.